opening of the web application. So it doesn't jump completely to the browser and disconnects you from SAP Mobile Start. You can jump back to SAP Mobile Start. So that's the case.
Okay, thank you so much, Robert.
Sure.
And with this, we are 1 minute over already. And again, a big thanks for everyone for joining. And we really hope you got a lot of value from this session. And Robert and Christoph, thank you so much for your excellent presentation and showing how to make the life easier of our users.
Thank you for having us.
Thanks a lot.
Hope to see you all soon again.
Bye.
Have a good day. Bye.
Have a great day. Bye-bye.
Take care.
Oh. Jetzt.
Okay, ja, ich würde ja nicht mal sprechen dürfen. Erstmal vielen Dank.
Wait a second.
AG. Very warm welcome, Paul.
Thank you, Lena.
Yeah, let's get started. The challenge is all about basically finding the right distance from two buildings at the SAP HANA campus. SAP campus in Waldorf, our headquarters. Let us know in the chat who has been to the campus before. That is basically what I'm interested in. So we know whether you have a rough understanding of how big it is. What was asked is that you imagine working in building 53 and you want to meet a colleague that is working in building 13. You want to meet basically in a equal fair share distance in the middle of the buildings, in a building, because you want to meet for a coffee. So it should be a building name and a distance that we're looking for as a solution for the challenge. And Paul and Bruno both found the right solution. And interestingly, it's been two different solution paths to the right exact same result. And that's what I found super interesting about it today. And that is how our call will be structured. So it will be Paul starting with introducing his solution, followed by Bruno introducing or sharing his solution. And then we have Markus from the SAP HANA Development Organization, our development architect, who is going to give you a little bit more insights and an outlook into the SAP HANA Cloud advanced multi-model capabilities. As always, we have 60 minutes and we have a dedicated Q&A towards the end of the session where we can address your questions in the chat. And I see the chat is already very lively with colleagues from Bruno, I guess, because it's in Portuguese. So Bruno chiming in here from Brazil. So thank you, everyone. Continue congratulating Bruno and Paul for winning the challenge. And I hope you have a lot of questions to our winners later on in the Q&A. I will definitely have some. And with that being said, I'll hand over to Paul, who's going to start sharing his solution first.
Okay. So let's quickly do that. So yeah, some words from my side. First, hello everyone again, and thank you for joining. As been said, my name is Paul, and I'm currently working with Avato in the smart data team. And actually, we are an IT consulting firm with our headquarters in Frankfurt, Germany. And we have, I think, some interesting projects in the Industry 4.0 and infrastructure context. And for myself, I'm right now a bit on a journey to become the person you have to talk to if you want to talk with Graph or want to have a Graph solution in our firm. So yeah, and personally, I do come from a chemistry background, so one could argue that I already worked with graphs before I knew that there are also graphs with databases. So let's start with my presentation. As you probably can see, I'm a huge fan of PowerPoint, so I try to put everything into one slide. This is about like the data we got. So how did I kind of got the data, build my graph coming from these 3 tables? Because I do like visualization, and I will just see if I can now find it. So I will introduce you to QGIS. If you work with spatial data, QGIS is actually a great tool to do. So here, as Lena pointed out, this is the campus. You can see it here. I mapped it out a bit for you. These are buildings, like the blue ones would be my source building, and this would be where I'm based, and this would be where my friend would be based. And then this the thing was to find one of these buildings. So all these colored, that's the valid target buildings. And I have to find one of them which has equal share between these 2 paths. So let's just have a quick look at one of these buildings. Takes a while. I have to take this away. So you have some attributes. This is actually, which I also like about QGIS, is actually live connection now. You have some attributes, and there's one of them I really need. This would be the nearest vertex. This gives me back my node ID, so I would probably need that one. Then I haven't shown you any graph yet, so let's quickly do that. I will upload all the vertices. The graph is normally, for those of you who probably joined and don't know so much about graph, it's made out of vertices which are connected by edges. So as you can see here, these vertices on the OpenStreetMap, they basically points. I can also have a look at them. So what do you need here? So there are some attributes, and the one I'm interested in would be like the OpenStreetMap ID, which will be my node ID later on. So what about the edges? I can also load them. So as you can see, the OpenStreetMap kind of represents the edges as line strings. So 2 nodes are connected via a line string. One node is connected via a line string to the second node. And if you stay in this terminology of OpenStreetMap, like a sequence of edges would be then referred to as ways. I will refer to them as paths later on. And as you can see, if I scroll a bit out, this is a subset of this OpenStreetMap data. And this would be virtually a graph, the whole graph, which covers more or less the whole Earth. And you can probably see that they all look really, really good connected. So there's a good data quality in here, which is normally not that granted. And so there are no dangling vertices, no dangling edges, looks all really good, really set up. So actually that was my graph. This is done. Going back in here. So now I built the graph. It's already set up. And now there was the challenge. Actually, I divided it for you into 2 parts. The first part would be a more technical one. So how do I do that? There are 3 graph languages which are provided or supported by HANA. One would be Paul Pfeiffer, the other one GraphScript, and then there would be calculation scenarios. I decided to use GraphScript because it's really well integrated into the HANA procedure, I think. So actually, with GraphScript, there's a built-in algorithm which is called single source shortest path. And this actually takes the source vertex and calculates the shortest path to a given target vertex. But to tackle this solution, I needed actually 2 paths. So would be one, as we've seen, the building would be my source vertex. Then I need a target vertex, and I need to do the same thing with the other friend's source vertex. So this could be done with GraphScript. Now, the only thing I had to do is to iterate over all the possible valid target vertices. This is nothing graph specific. I did that with SQL script, and I will show you also my script in a moment. So this was the first challenge. Was really nice, I think. I learned a lot. And then I had built a script which gave me back all the responding path lengths for every possible valid target. It's more or less a table. So then I thought, no, I just have to find the fair one. It's maybe an easy solution. Turned out to be not that easy at all. To be honest, not really solved it. So this is actually the second challenge, which is kind of a bigger one. A big part of it was that the thing about it was asked to get the fairest path. So I'm not an English native speaker, as you probably remarked. I looked it up for you, what is the concept of fair. As it with many like natural language things, it's already the concept of fair, or the definition of fair is ambiguous. So it would be treating people equally without favoritism or discrimination. This is what Oddfox says. So how do you now translate that to a simple program? It's a hard thing. I actually, on a side note, learned something else. The concept of fair in German is also called fair. But if you would address like a woman and would say you're a fair woman, you probably would not address her mind, but more her body. So yeah. So actually, this was a pretty hard task to do. So there are some very sophisticated concepts out there. If you're interested in like this pizza theorem or like a cutting pie theorem, but I needed something a bit more simple I could break down so I could get my program running. So I decided to divide my fair problem in two things. I have two boundaries. Actually, I thought that fair would be a trade-off between the most efficient path, would be the shortest path overall, and taking the most equal path. And I had to find something in between. So what I actually did, I introduced like a fair parameter into my script, which kind of, I wanted to also keep this ambiguity about fair, so that the person who uses my script can decide what is fair for him. So actually translating that to SQL, it's getting like a filter, which I would throw everything out, which I would consider unfair, and then I could resort the remaining path by the overall length. If that sounds a bit confusing, I will probably just show you how this is done. So we're going back to my HANA account. This is actually my script. I will run it. So let's just say this is my fair parameter. I'm a very altruistic person, or I'm not that busy. My friend is really busy, so I will be able to walk, like, let's say, put a higher amount, 2 kilometers more than the other one. So if we run that, if gives me back the name of the building would be VDF 53. So actually, you can now look that up in QGIS. Take that out. Zoom a bit in. And you see now that this will be actually just the path between these two buildings, because these two buildings also have coffee shops. So this is clearly not the solution. Let's try something else out. See, I like to work with this program. Let's say I'm really picky and I don't want to go 50 meters more than the other person. Let's just quickly run that. So this gives me back VDF 49. Let's just look that up in QGIS as well. I hope that will work. Yeah, it's also actually a good thing. This is actually live. So this gives me back this building. Looks already better. It's a building in between, but there's a problem with it, that actually I'm so picky that I would walk more distance than I would have done with the best solution. So how did I find the best solution? Yeah. If I put that to 100 meters and then I run it, this gives me the solution I found. It's VDF 4. We can also just see that. So this is the solution. There's another interesting solution I also would have accepted as solution, because I also would consider this fair. This would be if you put this to 300. No, it's not 2. So would be VDF2. Let's have a look. Why I would consider this solution also fair? It's actually on the original shortest path, so nobody has to do a detour to get there, and it's somewhere in between. So at that point, I have my script. You could probably just build a short IPA on top of it, and then you have a small calculator which calculates you or gets you a building. Yeah, let's just say I have another friend, and he's in building VDF7. I can run that. Have a look at it. And it would give me this building. Something I did not right. Yeah, if you do that live, I have to put it back to 100 because I actually want to get the fairest path. So it would give me this, and this I wouldn't have found if I would just have looked at the map. I would probably say that the building would be somewhere here, but I looked it up. It's actually the fairest thing. So I haven't showed you my script. We can go maybe a bit more into detail if you're interested in this. So actually, this what I did here. It's basically SQL script. So I had to define something. There's no graph specific about it, or nothing graph specific about it. So which is graph specific is actually this user-defined function. So this is a user-defined function I use to give me back all these corresponding lengths and the target vertex. So then I had to select the one I could consider fair, give it back to the function, and then I will call a procedure this time to give me back also the path. So I will just quickly show you the two functions if I still have time. So this is actually the graph thing. Yep. So now we set up. What you do here is you have to define some parameters, and then you have to define your graph here. There are some mapping I did to, or some container I built to set everything up. And the interesting thing is here is like this shortest path algorithm. Yeah, it actually takes mandatory. You need a source, you need a target. This has to be provided, and then it would calculate the shortest path. There's one thing about the HANA. You don't know, HANA doesn't know undirected graph. So if you want to traverse it on an undirected graph, because we're walking, so the direction doesn't matter, you have to specify it and say, okay, this has to do in any direction. There's another thing here, which is maybe interesting for those who also doing graph-specific stuff, that normally it would traverse the graph taking hop distance as weight. But I wanted to actually calculate the distance, so I had to return this attribute as length. Yeah? So you can, this is really versatile function, I think, because you can do also manipulate this thing. Yeah, I think Markus did I saw a really great video about some advanced graph topics where he also had like a shortest path function where you could even do some conditions in here. Yeah. So this shortest path gives me back a weighted path container. And this weighted path container is kind of a special container in GraphScript. So I use it here to give me back the weight. The weight would be the total sum of distances I just traversed. So then, because it's a user-defined function, I had to just to return the table. The second graph-specific function, this time would be a procedure. Now I'm doing more or less the same thing, but my weighted path also I can select every edge. I could also select every vertex. So it gives me back also a sequence with containing every edge. So that's what I used to construct these paths. This is more or less my presentation, and yeah, it has been really been a fun challenge, and I also want to thank that I felt really welcomed by the SAP community, and I hope there will be, I think it was the first challenge, I hope that will be some other challenges ahead. And I now will give over to Bruno, who has also, I think, a really interesting but different approach. So thank you, and see you later. So I have to stop sharing. Sorry about that.
Okay. Can I start sharing my screen and make my presentation? So let's start. Well, hello. My name is Bruno Affonso, and I'm a computer engineering and work as sysadmin, IT responsible, and SAP Business Web Consultant, and at Upper Tools, an SAP partner in Brazil, and challenge accepted. So, well, let's make a challenge analysis, right? First of all, we must define the shortest distance between the SAP WGF13 and WGF53. This distance, my concept of share is the distance must be traveled for both colleagues which be equal or close to be equal. And the meeting must be in a corresponding SAP building, right? So I plotted the vision of challenge too. I used the Beaver, the Beaver tool to make the plot on the map. And I think this is not necessary to solve the problem, right? But I think this is didactic. And if you work with as a teacher, as a trainer, or making learning, this is a good article to your listing of things to read. Well, the vertex table, this is a map of a part of the map of the all vertices available. I prefer to take print screen of the two because online in the live all things can happen, you know. So I prefer make a print screen. And we have 3010 vertex, same to the edges. Okay, we have 66,013 possible edges. And there is a table that represents the nearest vertices with the corresponding SAP building. Okay, and there is a restriction of type of the SAP building that can be used to the meeting, for the meeting. Okay, the shortest path. And so first of all, let's determine the shortest path between the 2 points. And there are, and that the sequence, I find it, okay. The sequence has 70 edges with this total length. Okay. And And with this total length, we must be fair, right? So let's divide this length by 2, and we get the middle length. Well, now let's make a mental work to assume the return of these functions. Okay, so first of this is the total edges counter, which in case we get 70, the total weight, which is this the total travel, the total length of the travel, and the last is our array, which contains each edge of each in the shortest path between the SAP, the 2 points. Okay, so we have the length of each edge with the total 70 edges, and this is part of my algorithm. And let's split into 2 parts to understand this. First, we have total edge counter, middle weight, and each edge length array, which is the return of the functions we haven't seen before, and they are fixed values. Okay, and we have the auxiliary variables too, which will be updated in each loop of this, for each loop. Okay, and each edge start with 0, and edge counter start with 0 too. The minimum difference is start with the maximum integer number possible. Okay. Okay, and we have to identify this. We need to get this edge index, which corresponds with the minimum difference. Okay, and this is represented by this column. So let's see the truth table to know what is happening. So in the first loop, we get the value of each edge, which is updated here. Is the current sum edges is 0 plus the first position of each edge length array, which is 50. So we store this value here, and the edge counter is incrementing. The if conditional will see if the minimum difference is greater than the absolute number between the difference between the middle weight and the sum each edge, which is true. So if it's true, the minimum difference will be updated with this value, and we get the index edge, the corresponding index edge. Okay, so we start again, and the values will be updated. The conditional will be satisfied, and this going on, rolling, keep rolling until for each edge counter is equal to the total edge counter, right? So break the loop, and we find a vertex. Okay, and we find a vertex. This is the vertex. Okay, the ID, the real ID. Just to illustrate, I keep a path between the corresponding vertex with the initial points. Okay, so this is the paths, But this vertex doesn't correspond with the nearest SAP building. So we get the shortest path function again to construct this grid, this array, and order by the distance, the total distance between the found vertex and all possibilities SAP building. And the order by this distance, I get a top 4 here, a top 4. It's sample is SAP WDF 1, 2, 3, and 4. It's just to illustrate 2. The difference between the SAP building and corresponding vertex. So with the selected top 4 minimum difference between the found vertexes and the vertex corresponding with the SAP buildings, which we found it, we get the top 4 SAP buildings and your respective length to SAP 13 and SAP 53. Nice, okay. And now from our 21 possibilities, we have already decrement to only 4 possibilities. So, well, to verify what SAP building are plausible and to analyze which SAP building can be used for the meeting, we sum each distance traveled for both of colleagues in a new column, which is the sum, and get these values. Okay. So, considering the best case just for reference, which is the vertex we found previously, in order by increase the sum, in order by the sum, we get this data set, and we find the SAP 2, which has equal value to our best case. Okay. So, but the length share must be fair. So so the difference traveled between the 2 colleagues must be equal or close to 0. So as can be checked of the best case is closer to 0. And the SAP WD2 has the best case, has the worst value of diff in our top sum of shortest distance. Okay, so we get the top 4 sum, right? Top 4 sum of the distance, and with this data set, with these 4 values, we order by the diff. We order by the sum and get the diffs. The diffs is the best of the sum is the worst of the diff. So we change the order and order by the difference num. So let's check the select top 3 order by the diff, and now with the top 4 order, right? Top 4 order by the sum selected before, and let's check the return. So we get this value. We get the WDF4, and we can check the best diff value. In other words, the minimum difference between the traveled between the colleagues. If we select the top 1, consider the short distance selected before, we get this value. So that's our answer, right? So from four possibilities, we can select top 1, order by the diff, and get this answer, our answer, our vertex. So the WDF4 has the only 2.3%, which represents 34 meters more traveled compared to our best case. So that's our answer, because he's the shortest distance possible and has the minimum difference too between the two travelers. Thank you all, and that's it.
Very good. So I will grab the screen and go next. Okay. My name is Markus. I work for SAP, and together with my colleagues, we made up this challenge. So listening to Bruno and to Paul, I think it became clear that this was not only a technical challenge, but also a conceptual challenge. So how to find a building in the middle, which is kind of fair for both colleagues to meet. Now, let me quickly share the solution that we came up with when we created that challenge. And like Paul, I thought this is a sorting problem. And like Paul, I came up with a two-step implementation. One step is a GraphScript procedure, which does the heavy lifting of calculating shortest path. And the other one is kind of an orchestration logic, where I join the data and I sum it up and I sort it. So let's take quickly a look at it. As I said, the third thing is a procedure I came up with. It takes as input parameters the set of buildings, the potential coffee places, and the building of the one colleague and the building of the other colleague. It is a procedure running in the database implemented in that GraphScript language. And what it basically does, it loops over all the buildings, all the potential coffee meeting places, and calculates two paths from the first building to the building in question, and from the second building to the building in question. And this is what these two calls to the built-in shortest path algorithms do. And the rest is just storing the result and returning path length and edges in specific. So calling the raw procedure gives me a result like that. So the nearest street vertex represents the potential coffee machines, and P1 and P2 are the length in meters which the two colleagues need to travel. Now, as I said, this is just the core of the logic, calculating all the path combinations. And the second logic is just a so-called anonymous block, a set of instructions written in SQL that allow me to aggregate and join the data and sort the data. So basically, what I did here is I called out to my procedure, receiving all the individual paths. Then I massaged the output a little bit, did a little bit of grouping and calculation. And then at the end, I just did a join and assembled my final result set. Now, the sorting criteria I came up with that, from my point of view, is a good approach to the best solution, a building in the middle, which is fair for both of our colleagues to travel, is by using the greatest function. And it basically allows me to minimize the longer of both paths. So this was my solution to the approach. Let's take a look at the processing logic here, and especially at the output. So what this means is building number 4 means I need to travel 680 meters if I'm colleague 1 and 770 meters if I am colleague 2. Altogether, these are 1,454 meters, which is clearly not the minimum sum of both paths. But it is somehow close when it comes to the difference of those both paths. So it's just unfair for 89 meters. And especially, and this was my sorting criteria, it minimizes the longer of both paths that needs to be traversed. And if we're looking here at some of the result visualizations, also using the Beaver's mapping capabilities, we do see the top three buildings here, including the paths to each one. So this might give you an additional understanding. So this was our approach to finding the building in the middle with the fairest share for two colleagues. But obviously, this is arguably maybe not the best solution. It's just one solution on how you can handle that. Now, moving away from the actual graph challenge, what we proposed, I wanted to show you 2 or 3 concepts that I discovered also when working on that solution, and that I thought might be worth sharing, essentially. The first concept is how to deal with table parameters in the GraphScript language. So remember, my procedure, one of the input parameters was the set of potential coffee machines, the set of potential meeting places. So the buildings table, so to say. You can use a table structure as input parameter, and there are a couple of things that you might want to do in GraphScript, having multiple values in a table. And one of the things that you might want to do is simply converting that table into a container data type in GraphScript, which we call a multiset. It's just an unordered set of variables. But what you can do with that multiset, where all the building IDs are stored, I can use it to filter my graph. I'm using that in-list predicate. So this is one of the concepts that you might want to do if you're dealing with multi-value, if you're dealing with a table input parameter. So if I quickly run that, it's not a lot value add behind that script, because it simply plots out the buildings, essentially. But it was a way to show how to use multisets derived from a table parameter in an in-list for filtering. Now, the second thing that you may want to do if you have a table as input parameter, you may want to loop over it. Again, I'm taking the same buildings table as input parameter. Again, I'm creating a multiset out of that table. And now I can use a for each loop to simply loop over all the values in my multiset, in my container, in my table. Now, this is also a concept which allow you to simply do a loop over multiple values that are provided to the procedure. Again, it doesn't make too much sense. Now, another way of looping over multiple values that are provided to the procedure, that are provided to the program, is simply by looping over the table directly. And for that, you can use a while loop. And for the parameter, increasing parameter here, you are counting from 1 to the count, which means the size of my input table. And if I want to refer to rows in my input table, I'm using that index-based table approach. So I'm saying, okay, in this case, I'm creating vertex, and I'm using one of the provided integer values in my table. And the way I access that table is by using that index I over here, which is my Laufvariable. Now, the final thing that I might want to show you, which comes in handy, so far, I've only looked at one column of my input table and converted that to a multiset, or looped over the table and accessed that value. Now, what if you want to create a more suitable type of a data structure, a map data structure, which essentially gives you key value pairs and allows you to access the values for providing the keys? And this is currently supported by using that map container. So a map is a 2-column data structure you can think of, keys and values. And I want to put my buildings in that map data structure, where for the building key, so to say, I'm also storing the building name WDF04, for example. So I'm filling up that map, and I'm using that map for example, here also now in a for each loop in order to create or project the output. And this is how we loop over a map. You simply can refer to both the key as well as the value in your map. Now, the last thing that I want to show is a new traversal operator, which is called traverse Dijkstra. And one of the core problems that you can solve with that traversal strategy is things like top k nearest neighbors. So think about a problem. You're on a street network and you want to find the top 3 gas station on that street network. So one way how you could approach that is using breadth first search traversal. So essentially starting at a vertex in your graph and then traversing out, stepping through the graph in a hop by hop manner, breadth first search. And checking if you reach the gas station, then doing something with it. So this is a built-in traversal statement, built-in traversal operation, which is the core or the foundation for many graph algorithm, many graph procedures, breadth first search. Now, the problem with breadth first search is that it traverses, expands in the graph in a hop by hop manner. So obviously this is not very suitable if you're dealing with a weighted graph, where the edges, for example, have a length, like in our street network, where we have the length of the edge segment here. Now, a second approach you could choose to answer the question top 3 gas stations is you could calculate a shortest path from your starting point, your current location, to all other nodes in the graph, and then filter out afterwards just for the gas station and then maybe order for the top 3. This is for sure possible, but if your network is really, really large, you calculate a lot of shortest path one to all, which might not be optimal from a performance perspective because you cannot stop this traversal essentially. Now, this is why we introduced the traverse Dijkstra operator. It starts at a vertex in the graph, but doesn't do hop by hop expansion or hop by hop traversals, but it traverses the graph in a kind of a shortest path manner. So just expanding the node first, which is currently reached by the shortest path. And this kind of gives us a way to solve the top k gas station problem. So this is how that would look like. So I'm starting from a node in my graph. I'm traversing in a shortest path manner, in a Dijkstra manner. And what this allows me to do is essentially use a hook function. Whenever I visit a vertex in my shortest path traversal, I can inspect that vertex. I can say, are you a gas station? And if I found a gas station, I put it in my result set. And if I found 3 gas stations, I stop the traversal. So I'm not traversing the complete graph, but I'm just traversing as long as I'm still looking for additional gas stations. Now, bringing that to life in our scenario, you might want to think about, okay, our 2 colleagues met in WDF4, which is the most fair building in the middle, but the coffee machine is broken. And so they are looking for an alternative. So now they're in WDF4 and they say, okay, where can we go? And let's maybe evaluate the top 3 or something, or top 5 nearest SAP buildings from where we are currently. And so the way I implemented that is as an anonymous block, so providing simply the input parameters here directly. I'm starting from WDF04. I'm again handing in all the potential buildings that host the coffee machine. And I'm looking for the top K, top 5 nearest building with a coffee machine. So in the end, this comes down to a traverse Dijkstra statement, where I'm starting from WDF04, traversing in the nearest path manner. And whenever I found a building which is suitable because it hosts a coffee machine, I simply put that building in my output data structure. And if I found more than K, more than 5 requested buildings, I stop the traversal and the procedure terminates and the result is being handed over. So let's take quickly a look at the results of that procedure. What it basically gives me is the top K, top 5 nearest buildings, including their distance. And for each of the building, I can also take a look at the individual edges that make up the specific path. So it returns K shortest path from my start node to the K5 nearest buildings, which I found. So that basically concludes what I wanted to show in addition. To sum that up, I think both Bruno and Paul did a great job solving the PM challenge, despite the fact that there was room for interpretation when it comes to understanding what fair or best solution means. I came up with the solution of sorting the potential solutions by minimizing the larger of the 2 paths our colleagues traveled. I showed you a little bit how to deal with table input parameters in GraphScript program, using these table input parameters, this multi-value table, so to say, as a way to filter, or as a way to run loops, or as a way to fill in a map data structure. And last but not least, I showed you the new traverse Dijkstra statement as a way to traverse a graph in the shortest path manner, so to say, especially to solve top K nearest neighbor problems. That's it from my side. Maybe back or over to Lena and see if we have additional questions.
Thank you, Markus. Thank you, Bruno. Thank you, Paul, for presenting your solutions. Very interesting, very detailed also, that deep dive from you, Markus. Bruno, Paul, you can come back on camera for the Q&A. We have a very lively chat. Not so far too many questions. A lot of congratulations to both of you. Basically, it seems like every single participant in this call actually congratulated in the chat. Love that one. So also again, from my side, congratulations. I have 2 questions, as I said in the beginning, that I wanted to address to you. And please, community, shoot your questions to Bruno and Paul if you have. Mine was how you actually heard about the challenge, first of all, and since when are you working with SAP HANA Graph?
Shall I go first?
Yeah, sure.
Yeah, it was actually a colleague showed it to me, and I started working 6 months ago with Graph, and yeah, also 6 months ago with HANA.
Well, I always see the updates, SAP updates on social media and blogs, and always try to know what happened in SAP world, you know, and this challenge came to me probably in one of social media or read the blogs. And I confess I started work with HANA Graph 2 weeks ago, and I make the challenge. I have make some workshops with SAP BTP, SAP HANA Cloud, and with some SAP people. And when the challenge appears, I see the opportunity to learn more. So I did it, and I answered and sent an mail, and here I am.
And here you are, winning the SAP HANA Graph Challenge.
Yeah.
Impressive that you just started 2 weeks ago. Very impressive. But also 6 months ago. Wow. Another hint, as I just figured that you found out about the challenge via social media, is definitely following our tag SAP HANA Graph in the community. so you can get notifications when there is new blog posts, such as Susan's blog post. I posted it already in the chat. Have a look, please. Is published on the SAP community. So I'll share the slide deck of the call today will be added to the YouTube description in 2 to 3 days, where we share links to the SAP community tags for SAP HANA Graph. So stay tuned for a potential part 2 of the challenge. Paul mentioned that he would look forward to another challenge, maybe a similar one. In the meetings that we had prior to the call, I figured that you found that fairness definition interesting. So, and there were a lot of more detailed conversations with Markus and Paul about that fairness and statistical studies or about it as well. All right. We have a few more minutes before we end the call. Any more questions from the audience to Bruno and Paul? Content-wise, all clear? We have a lot of hashtag upper tools in the chat as well.
Yeah.
All right. In case you want to reach out to Bruno and Paul and Markus, I posted their profiles in the chat. So let me thank you all for your time and for presenting to the SAP community, for sharing your solution, for explaining your solution. I hope that now sparkled the interest of some of our community members to also learn SAP HANA Graph, when we now know being a brain like Bruno, only learning it within 2 weeks. So yeah, check it out. Follow our tag SAP HANA Graph and join us for our upcoming SAP community calls. Have a good one, and I'll see you soon.
Thank you, Lena.
Yes, thank you for the opportunity.
Thank you.
And wait for the next.
Bye, Bruno.
Bye.
Exactly.
Bye. Thank you.
Thank you. Bye-bye.